All right, this is Tuesday, February 23rd, 2021. I'm going to do a debrief for Physics CP on centripetal force and the universal law of gravitation. Homework 2 says the equations you need, centripetal acceleration. That one says v squared divided by the radius of a circle. And by the way, all this homework is going to be for circular orbits or circles. The acceleration towards the center-seeking acceleration is the square of your speed divided by the radius of the circle. Another way to write the same formula is 4 times pi squared times the radius of the circle divided by the period of time squared that it takes to go around the circle once. That's centripetal acceleration. Centripetal force, that equation is the mass times centripetal acceleration. So it's a version of Newton's second law, F equals ma. It's just here the centripetal force is equal to mass times the centripetal acceleration. And Newton's law of universal gravitation says, give me any two objects in the universe, and we can calculate the gravitational pull between them. Pull is an attraction, so we write it with a minus sign. It's the product of capital G, the universal gravitational constant, times the first mass, times the second mass, and the order doesn't matter, divided by the distance from the center of one mass to the center of the second mass squared. And the one constant, capital G, has a value of 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared. So anytime that you use these formulas, they're really set up for you to convert them into units of kilograms and meters and seconds before you plug them into any kind of formula. All right, here we go. Problem number 1. Whoops, a little zoomed in. Whoa, it's hard to get this just right. After all these years of teaching, I still don't get it. Okay, the Earth has a mass of 5.974 times 10 to the 24th power kilograms. The NSS-6 Earth orbiting satellite has a mass of 4,575 kilograms and is located in a circular orbit with a radius of 42,164 kilometers. Calculate the gravitational force of attraction between Earth and the satellite. Well, for that one, we're going to be using Newton's law of universal gravitation. Force of gravitational attraction is equal to negative g times the first mass times the second mass divided by the distance between the two of them squared. The only thing you have to notice is that the units for distance are given in kilometers. Of course, you know that 1 kilometer is equal to 1,000 meters. So you better express 42,164 kilometers as 42,164,000 meters before you square. All right, so with my handy dandy calculator, which you can see the display a little bit now, G is already programmed. The first mass is the mass of the Earth, 5.974 times 10 to the 24th power. Then multiply that by the mass of the satellite, 4,575 kilograms. Then divide that by 42,164,000 squared. Enter. All right, so there's the answer. The 3 sig figs. The force of gravitational attraction is minus, meaning it's attractive, 1,030 newtons. Ta-da! There's the answer to number 1. And by the way, if you were to Google it, this is the actual name of the satellite at that location around the Earth, and it's an estimate of its mass after it's used a little bit of its fuel. Okay, you don't care. Number 2, the NSS-6 Earth orbiting satellite has an orbital speed. Wow, this is so wrong. Oh, I said the wrong thing. Has an orbital period, not speed. Now it's correct. Has an orbital period of 86,164 seconds and is located in a circular orbit with a radius of 42,164 kilometers. That's because I didn't make it up. These are where it really is and the data that really is about it. Calculate the centripetal force acting on a satellite, and the satellite still has a mass of 4,575 kilograms. Centripetal force is mass times centripetal acceleration. I do not have the speed of the satellite. I do have its orbital radius and its orbital period. So I should select this version of the centripetal acceleration. So it's going to be mass times 4 times pi squared times the orbital radius. Again, it's in kilometers, and you need to convert kilometers to meters first by multiplying it by 1,000, and then divide it by the period squared. All right, well, so the mass is 4,575 kilograms. I'm going to multiply that by 4. I'm going to multiply that by pi squared. I'm going to multiply that by 42,164,000. I'm going to divide all of that by 86,164 squared. Enter. And oh my goodness, look at how very, very, very similar the two results are on my calculator. And that's not a coincidence. So the centripetal force needed to keep the satellite in orbit has a magnitude of 1,030 newtons. And to 1, 2, 3, 4, 5 sig figs, they're identical values. And we're only calculating it to 3, so they're identical values. Number 3, the mass of Mars is 6.399 times 10 to the 23rd power kilograms. The mass of the Hope satellite orbiting Mars, which I believe is a Chinese spacecraft. I don't know. It's not American, though. It could be an Arab satellite. So I'm trying to use actual data from actual space missions going on right now. The mass of the Hope satellite orbiting Mars is 955 kilograms. Its orbital radius is an average of 34,970 kilometers from the center of Mars. And we always measure orbit radius from the center of the object. Calculate the gravitational let's make that force of attraction between Mars and the Hope satellite. So this is identical to problem 1. We're going to use Newton's law of universal gravitation that says the attraction gravitationally is the product of the universal gravitational constant times the mass of Mars times the mass of the Hope satellite divided by the distance from the center of Mars to the center of the Hope satellite squared. And as before, we're expressing the distances in units of kilometers, which means this is 34,970,000 meters. All right, well, let's see what we get. G times 6.399 times 10 to the 23rd power. Whoa, what did I type in? Times 10 to the 20, I guess I'm in alpha lock. 23rd power Actually, all of that is wrong. Okay, so G times 6.399 times 10 to the 23rd power times 955 kilograms for the Hope satellite divided by 34,970,000 meters squared, enter. And there's not much force going on there. It says the force of gravitational attraction between these two objects is negative because it's attractive, 33.3 newtons. You could push that. Negative 33.3 newtons. Number 4, there's a pattern to the way I created these problems. Let's see if you can notice it. The Hope satellite orbiting Mars has an orbital period of 55.00 hours. If the mass of the satellite is 955 kilograms and its orbital radius is 34,970 kilometers, same values, calculate the centripetal force acting on the satellite. Well, centripetal force is going to be m. I don't have the speed, although I could calculate it by taking the radius, multiplying that by 2 pi to get the circumference, dividing the circumference by the time it takes to go around it once, and I would have the speed from that. But I'm going to do the other version that says 4 pi squared r divided by t squared. Of course, being in hours, you have to convert the hours to seconds. You're expected to know that there's 60 minutes in an hour and 60 seconds in a minute, or otherwise 3,600 seconds in an hour. And of course, if the radius is in kilometers, you need to convert it to meters before you plug it into the formula. Here we go. 955 times 4 times pi squared times 34,970,000 divided by, open parentheses, 55 hours times 3,600 seconds per hour, close parentheses, squared, enter. My goodness. We have almost exactly the same value once again. So the centripetal force acting on the satellite has a magnitude of 33.6 newtons. Why is there a discrepancy? Probably because I rounded the hours to 55.00 when it was maybe a few seconds different from that in value. Maybe it was. So what you should notice, having done your homework this far, is that the gravitational force of attraction for an object in orbit around another object happens to be equal to the centripetal force keeping that object in a circular orbit. Same result if you look at these two numbers. The gravitational force of attraction between two objects, one orbiting the other, is not coincidentally equal to the centripetal force needed to keep one object in orbit around the other. All right, so number 5, the last question. The Hope satellite orbiting Mars has an orbital radius of 34,970 kilometers and a period of 55.00 hours. Calculate the orbital velocity of the satellite in meters per second. There's 2 ways you can solve this problem. The first way is just old-fashioned math class that says, oh, I know in a straight line the distance that I travel is equal to the product of my speed times the time I spend going at that speed. So for example, if I'm going 20 miles per hour for 3 hours, I know I've gone, 20 times 3 is 60 miles. If the units are meters per second and seconds, I'll get a distance in meters. When I go completely around the circle once, I've traveled a distance equal to its circumference, 2 pi r. And the time that it takes for me to go around the circle once is the period. So I could calculate the orbital velocity of the satellite using old-fashioned geometry that says 2 pi r divided by the period will get me the right answer. In this case, 2 pi, again with the meters to kilometers thing. So 34,970,000 meters divided by, again with the units thing, I have to convert 55 hours into seconds by multiplying by 3,600 seconds per hour. And that will give me an answer. Let's see. 2 pi 34,970,000 divided by, open parentheses, 55 hours times 3,600 seconds per hour, close parentheses, enter, and I get an orbital speed of 1,110 meters per second. And that works. Ta-da, I have an answer. So you don't have to freak out that I'm doing orbital mechanics with you. You can do stuff as you understand it. Now, the other way you can get to the same answer would be to say, oh, let's use the formula for centripetal acceleration, perhaps. I'm thinking. It's just that in this situation, I didn't actually give you the centripetal acceleration. What I did give you is actually what I did not give you is a formula that says v squared equals g times m divided by r. I'm not sure you had that formula at the time that this problem was assigned. If you did, then you use the mass of Mars and the orbit radius, take the square root of this, and you'll have the speed. I'll do it for you just to show you that yes, that works. Take the square root of g times the mass of Mars, which was 6.399 times 10 to the 23rd power. Divide that by the orbit radius, which was 34,970,000. And to a slight difference. The difference is within the third sig fig. So this way it would have rounded down 1.10 times 10 to the third power meters per second. Okay, so that's the result using that information. And then finally, what if you just tried to do it hopefully algebraically, that says if v squared divided by r is equal to 4 pi squared r divided by t squared, eventually, if you multiply both sides by r, you get v squared equals 4 pi squared r squared over t squared, and you take the square root of both sides, and you have v is equal to 2 pi r divided by t, which is where I started from with geometry. All right, so, and we know that answer is 1,110 meters per second. Ta-da! this concludes this debrief.